Hello everyone and welcome to another video. Last time we talked about what a U-sub is, why it works, and we explored a quick example of using it to solve an integral. Now today I want to continue practicing with the U-sub and show some more applications of it. Let's take a look at this integral. The integral of cosine of x squared inside the parentheses. Okay, so how do we go about this? Well, we actually can't. Sorry, this isn't a solvable integral with our current tools. However, I'm going to add a 2x right here. And we're going to make this integral the integral of 2x times cosine of x squared to dx. Wait, but why would we make another function inside the integral? I mean, that just seems like it's complicating things. If we couldn't do the cosine of x squared already, then why does this make it possible? Well, that's because we can't integrate cosine of x squared with respect to x, but we can integrate it with respect to 2x dx. What does that mean? Check this out. If we make a u-substitution and we set it equal to x squared, taking the derivative of both sides, we'll get du dx equals 2x, meaning du equals 2x dx. Okay, what the heck does this mean? Well, it means that for every slice of dx, every tiny, infinitely small slice of x, if we multiply by 2x, then we'll get a properly small slice of u, the chunk that is du. Okay, well, what does that mean for the integral? It means that we can do this. Making those u substitutions, we see that if du equals 2x dx, well, we have a 2x dx. We have 2x right here, and we have dx right here. So we can combine these to make a du, and then cosine of x squared, well, we made u equal to x squared. So we now have the integral of cosine u with respect to u, du. Now for this integral, we should already understand how this can be possible. If the derivative of sine is cosine, and the integral is the antiderivative, sine to cosine, going backwards, we get cosine to sine. So the integral is going to be sine of u, plus c. But we're not done because this is in terms of u, so we're going to make sure we have it back into our x form, so u is equal to x squared, so we just plug that in. We get sine of x squared plus c, and there is our final answer. For the next example, we're going to be integrating sine x cosine x. There are a couple of ways to do this actually, one involving a trigonometric identity, but because of the purpose of this video, we're going to be doing it by u-substitution. So, where can we use a u-substitution? The last time we substituted in the inside of a function, the argument, to make sure that something on the outside could combine with the dx and make a du. So what can we do here? Well, last time we had an x squared and a 2x, and since 2x is the derivative of x squared, we were able to make it work with the du dx. Now for this, we can actually see a similar thing. We have a function and the derivative of the function both inside the integral. Cosine x is the derivative of sine x, meaning if we let u equal sine x, then du dx will equal cosine x, and so I'm going to multiply the dx on both sides, and we get this expression, that du equals cosine x dx. Wait a minute, where have we seen that before, right? It's right there, which means we can rewrite this integral now. Sine x is just u, and then cosine x dx collapses to just be du. So this is our new integral. Now this is a very nice, easy integral, right? It's just the reverse power rule. So what are we going to do? We're going to have our u, and then we're going to add 1 to the power, and then we're going to bring it to the front, dividing. All right, and then plus c, and we're not done because we need to go back to the x world. U equals sine x, so we'll plug that back in here. We get our 1/2 sine squared x plus c. And that is our final answer for this integral. So the whole idea of a U-substitution is to look at something inside of the integral and see if you can have a something and a derivative of that something, both inside the integral. Now, to illustrate this point, I want to work through one more integral. Now, this next integral is the last one, but this one looks pretty gnarly, right? Negative sine x times cosine of cosine x. What the heck, a nested cosine? That's weird, right? Well, what we're looking for, remember, is always a function and a derivative of that function, both inside the integral. What do we have? Well, we only have sines and cosines, and we know that those are each other's derivatives. So, let's look. All right, well, cosine of cosine x. I don't really want to deal with that. I don't really want to look at that, right? Inside here is just a cosine x. Now, that's easy. We can deal with that. We know what the derivative of cosine x is. It's negative sine x. Oh, hey. Look at that. How convenient, right? So, what we'll do is we'll let u equal cosine x, which means du will equal negative sine x dx. Now, this is the same thing. Du dx is equal to negative sine x, and then you multiply the dx across both sides. So, what does that mean for us? Well, we can rewrite this integral. Negative sine x and dx will combine to make du. So now we're left with just this, cosine of cosine x. Well, cosine x is just u. All right, nice. Let's sub that in. Cosine of u. And then all we have left is the du. All right, well, we talked about this already. The integral of cosine is just sine. So we know this is going to be sine of u plus c, except we want to get back in the x world. What's u in terms of x? U is equal to cosine x. So the solution of this integral is going to be sine of cosine of x plus c. And this will be our final solution to this integral. So, all you have to remember for U-substitution is you look at whatever is giving you trouble and you try to find if there's a function and a derivative of that function inside the integral so that you can U-sub and re-parameterize everything in there to make it much, much simpler, much, much nicer, and then you just have to translate back into the X world at the end. I hope you were able to follow along with the examples today. I encourage you to look elsewhere, look beyond, practice with your own examples, and thank you so much for watching.